In this lecture video, we look at example 5.5, where we demonstrate how to perform an analysis of variance for a two-factor complete factorial treatment structure. So here's a description of the scenario. So consider again the experiment described in example 5.4. Suppose that the three tree varieties used in the experiment were actually a random sample of varieties selected from a larger population of varieties, and that the experimenter wants to make inferences not about the three varieties used in the experiment, but rather about the entire population of tree varieties from which the three varieties were randomly selected. In this case, tree variety is a random effect, and the analysis of variance performed in example 5.4 is not applicable. The three pesticides selected by the researchers are the only pesticides of interest. Now perform an analysis of variance to determine whether there are differences in mean fruit yield due to pesticide or tree variety, where pesticide is again a fixed effect, but where tree variety is a random effect, and the inference with regard to variety is to the entire population of tree varieties. Use a significance level of 0.05 in all tests. Now in this situation, most of the calculations are the same as they were back in example 5.4, where both factor A, pesticide, and factor B, tree variety, were fixed effects. The only quantities that need to be considered for changing in this situation are the F statistics. Now in this situation, factor A, pesticide, is a fixed effect, and factor B, tree variety, is a random effect. Also, since at least one of the two factors is a random effect, their interaction is also a random effect. In order to calculate appropriate F statistics that test what we actually want to test, we need to consider the expected values of the mean squares in this case. Now, what are the hypotheses that we want to test? They're on the next slide. Let's take a look. So these are the three hypotheses we want to test. In the first test, the test for the fixed effect of factor A, the null hypothesis that we want to test is that all alpha sub i's are zero against the alternative hypothesis that at least one of the alpha sub i's is not equal to zero. In the second test, the test for the random effect of factor B, the null hypothesis is that the variance of factor B is zero against the alternative hypothesis that the variance of factor B is non-zero. Right? It's greater than zero. So since factor B is a random effect, since tree variety is a random effect, we need to express the hypotheses in terms of the variance of that factor. And then finally, at least in this list, the third test is the test for the random effect of the AB interaction. And because at least one of factor A and factor B are random effects, the interaction term is a random effect as well. And so the null hypothesis, which essentially states that there is no interaction between A and B, is expressed in terms of the variance of the random effect of that interaction. So the null hypothesis says that the variance, sigma squared alpha beta, is equal to zero, against the alternative hypothesis that says that the variance, sigma squared alpha beta, is greater than zero. And that alternative hypothesis expressed in words is basically saying that there is interaction between pesticide and tree variety. Now, in order to come up with the appropriate F statistics for these tests, we need to consider the expected mean squares. Now, in a previous lecture video, we showed how to do this, and using that approach, we can come up with the appropriate F statistics that we have here. The F statistic for the overall significance of treatments is MST over MSE. The F statistic for the fixed effect of factor A, F sub A, turns out to be MSA over MSAB. The F statistic for testing the significance of the random effect of factor B, so F sub B, is MSB over MSE, And the F statistic for testing the random effect of the interaction is MSAB over MSE. So of the 4 tests here, the F statistic for testing the fixed effect of factor A is the one that looks a little different because it has MSAB in the denominator. So here was the basic ANOVA, and we did this back in example 5.4, and the F statistic in this ANOVA table is testing this first F statistic, the F statistic for the overall significance of the treatments. And remember, we can consider this as a gatekeeper test because it's testing all of the other factorial tests simultaneously. And that F statistic is 14.3601. And we see here the hypothesis that's being tested by that F statistic, expressing it in terms of the factorial effects. And so the null hypothesis says that all alpha sub i's are 0, and the variance of the random effect factor B is 0, and the variance of the random interaction effect is also 0. The alternative says, it's the logical complement of the null, obviously. It says that at least one of the alpha i's is non-zero, or the variance of the random effect for factor B is greater than 0, or the variance of the random interaction effect is greater than 0. The significance level we're going to use is 0.05. The critical point is the upper fifth percentage point of the F distribution with 11 numerator degrees of freedom and 12 denominator degrees of freedom. And from the table, that is equal to 2.72. The test statistic, F sub t, is the ratio of mean square for treatments to the mean squared error. That turns out to be 14.3601. The p-value for the test is 2.955 times 10 to the minus fifth. And since the F statistic is greater than 2.72, or equivalently, since the p-value is less than or equal to alpha, we reject the null hypothesis and conclude that at least one of the factorial effects is impacting the response, either factor A, pesticide, which is a fixed effect, or the random factor B, the tree variety, or the random A by B interaction. It therefore makes sense to test the significance of the factorial effects. So again, we're using this test of the overall significance of treatments as a gatekeeper test to inform us as to whether it makes sense to proceed in looking at subsequent tests. And so we are going to now look at the expanded table, which we've already done the calculations for. The only thing that we need to potentially recalculate would be the F statistics. And you'll recall from a previous slide that these are the formulas we need to use for those F statistics. So just make sure that when calculating the F statistic for factor A, that we divide MSA by MSAB rather than MSE. Okay, and so those are the F statistics for factor A, factor B, and the interaction. And so testing, looking first at the hypothesis test for the random effect of the AB interaction, the null hypothesis is that the variance of that random interaction term is 0 against the alternative hypothesis that the variance of that random interaction effect is greater than 0. We're using a 0.05 level of significance. The critical point is the upper fifth percentage point of the F distribution with 6 numerator degrees of freedom and 12 denominator degrees of freedom. We have 6 denominator degrees of freedom because there are 6 degrees of freedom associated with MSAB, which is the numerator of that F statistic. And we have 12 denominator degrees of freedom because there are 12 degrees of freedom associated with the mean squared error, which is the denominator of the F statistic. The test statistic value, well, the critical point itself is 3.00. The test statistic is 1.8007. The p-value, which I calculated using the TI-84 calculator, is 0.1817. And therefore, we can see that we fail to reject the null hypothesis that the variability associated with the random effect of the A-B interaction is 0. And so that's equivalent to saying we fail to reject the assumption that there is no interaction between pesticide and tree variety. And so it's meaningful to proceed to the subsequent tests involving the main effect of pesticide and the main effect of tree variety. Okay, so next, let's look at the hypothesis test for the fixed effect of factor A. And so the null hypothesis is that all the alphas are 0 against the alternative hypothesis that at least one of the alphas is non-zero. We're going to use a significance level of 0.05. The critical point is the upper fifth percentage point of the F distribution with 3 numerator degrees of freedom and 6 denominator degrees of freedom. Now we have 3 numerator degrees of freedom because there are 3 numerator degrees of freedom associated with MSA, which is the numerator of the F statistic. And we have 6 denominator degrees of freedom because there are 6 degrees of freedom associated with MSAB, which you'll see here is the denominator of the F statistic. All right, so that critical point turns out to be 4.76. The F statistic itself is 9.75, and the p-value is 0.0101. So in this case, we see that we would reject the null hypothesis that the factor A main effect is 0, all right, and follow-up comparisons of those pesticides would be warranted. So we've got 4 levels of pesticide, and so we would be justified in doing perhaps pairwise comparisons or something like that. All right, and then finally, looking at the hypothesis test for the random effect of factor B. So the null hypothesis is that the variance of the random effect factor B is 0 against the alternative that the variance of the random effect factor B is greater than 0. We're going to use a 0.05 level of significance. The critical point for the test is the upper fifth percentage point of the F distribution with 2 numerator degrees of freedom and 12 denominator degrees of freedom. We have 2 numerator degrees of freedom because there are 2 degrees of freedom associated with MSB, which is in the numerator of the F statistic, and we have 12 denominator degrees of freedom because there are 12 degrees of freedom associated with mean squared error, which is in the denominator of the F statistic. The critical point is therefore 3.89. The test statistic value is 47.2443, and the p-value computed with the TI-84 calculator is 2.0477 times 10 to the minus 6th. And so we see that we would reject the null hypothesis and therefore conclude that the variance of the random effect factor B is positive. There is variability in the mean response in the population of tree varieties. All right, so the overall conclusions regarding the factorial effects. The assumption of no interaction between pesticides and tree varieties is not rejected at the 0.05 level of significance, and so moving forward through the analysis, we're justified in carrying that assumption along with us, doing the subsequent analyses assuming no interaction. The pesticide main effect, which is the fixed effect, is significant at the 0.05 level of significance, and so because of that, comparisons amongst the 4 levels of pesticide would be justified. And finally, variation exists in the response across the population of tree varieties, not just amongst the tree varieties used in the experiment, but again, this inference extends to the entire population of tree varieties from which the 3 tree varieties used in the experiment were selected from. And so we conclude that at the 0.05 level of significance, there is variation in the response across the population of tree varieties. Okay, so that's the end of this example, and I included this to show that we do have to take care in how we do the analyses. We have to consider we have to consider the nature of the effects. Are the effects fixed effects? Are the random effects? The inference space of the experimenter and how they selected the levels of various factors to include in the experiment impacts the appropriate way for calculating F statistics and the inferences that we can draw then.